All right, I'm back. We're on page 311, and we're talking about critical point. So critical point in the domain at which, of the function at which the derivative is equal to 0 or does not exist. If you watched the last video, you saw me completely mess up a problem, go back and hopefully fix it. The issue was manifold. There were a lot of problems there. But anyway, we're back. We're going to try to do this. So first problem, approximate the critical points of f of x equals x cubed minus 5x plus 3 sine of x squared. What? Over the interval from -2 to 2.5 using your calculator. Show work. All right, so critical points. Points in the domain. Looking at that function, you can tell that there are no points that aren't in the domain. So our critical points will be points in the domain at which the derivative is 0 or the derivative is undefined. So, all right. So I'm going to start off by saying that we want critical points f prime of x equals 0. And then I'm going to let the calculator do the work. We're going to find that there are no points. So I just happen to know this, and you'll know it pretty soon too. There are no points where f prime is undefined. So we don't really need to worry about that. Let's go to the calculator and see what we can do with this thing. So share this. This is the graph that gave me so much trouble in the last video. I'm going to start a new document, put that in the past. F of x is x cubed minus 5x plus 3 sine of x squared. Okay, so this is our function. We want the critical points on the interval from -2 to 2.5. Let's just see if the calculator can do it, right? So let's do menu 3, 1. We're going to try to solve the derivative. So the solve does not love trig functions, but sometimes it does. So we want to know when the derivative is equal to 0, we want to solve for x, and I want to restrict this. So I'm going to hit Control and equals, go such that -2, and then Control equals. So notice I'm outside of the parentheses for solve. That's essential. Otherwise, the calculator will just outright ignore it, and it won't even give you a warning or anything. It just totally ignores what you did. Less than or equal to 2 point that, less than or equal to 2.5. And let's see, we get 1, 2, 3, 4 different critical points. Now, calculator is probably telling me that more solutions may exist. Let's see. More solutions may exist. Try to specify. I usually take it to mean try graphing, because I don't try. As soon as it says that, I'm like, man, what if there are more and I just don't see them? So let's go to graph. I'm going to graph the derivative. So let's see, derivative with respect to x of f of x. Let's change the window. Menu 4. All right, so we only are interested in -2 to 2.5. And then the y values don't really matter because we only need to see the zeros of this thing. So let's say this. All right, so 1, 2, 3, 4. There are definitely 4. How could I find them on the graph page? Press tab, add 0. I'm going to do menu, 8, 1, and option 4 for intersection points. It's option 3 on a lot of calculators. What the? Why are you letting me pick that up? I want to undo that. So for some reason, it let me pick that up. Menu, 8, 1, 4, click, and click. And what? I don't really know what happened there, but here we go. So that's interesting. I had some technical difficulties. Also, I already found these on the calculator page, so I could potentially have just taken the answers from the calculator page. But now I got to jot these down. Okay, so I'm going to switch back to the notes, and then I'm going to surreptitiously switch back to the calculator so that I can actually see the things that I need to write down. But you can watch me write, I suppose. All right, so let's see. We're going to go 3 decimal places, and what you're going to do is you're going to put them in order, because that's what civilized people do. So it's going to be x is approximately -1.264, x is approximately 0.674, 0.6. I always put the leading 0. I think it's important because then, it's way more obvious that that decimal point was there. 1.227, 1.227, and x is approximately 2.0 2.018. 2.018. All right, so these are our critical points. So there's 4 critical points. I'm going to take you back to the calculator so that we can look at the graph again and just kind of like walk through what's happening on the function at these critical points. All right, so this is the graph of the derivative. So the derivative changes from positive, because we're above the axis, to negative at negative 1.264, which means the function will have a relative maximum because the function changed from increasing to decreasing. So this x-coordinate corresponds to a relative maximum on f of x. At 0.674, the derivative changes from negative to positive, so the function changes from decreasing to increasing. That's the x-coordinate of a relative minimum. The next one will be a relative maximum because the derivative is changing from positive to negative, and then we'll have another relative minimum. I don't know if I said maximum here, I meant to. It's a maximum at 1.227 because the derivative changes positive to negative, and then we're going to have a relative minimum at 2.018 because the derivative changes from negative to positive. Let's actually graph f of x on the same set of axes and see what it looks like. All right, so f of x is in black here, and I'm just gonna zoom a little. Actually, I'm gonna delete these so that they're not in the way, just messing things up. It's too much on the screen, you know? And delete. Okay, so we said that this x-coordinate would be a relative maximum for f of x because f prime was changing positive to negative. Look at f of x, you can see the maximum. We said this would be a relative minimum for f of x because the derivative changes negative to positive. It's very subtle, but you can see that there is a minimum in there. This should be a relative maximum because f prime is changing positive to negative. And on the graph, you can see it. It's kind of subtle, but it's there. And then finally, we said this would be a relative minimum because f prime is changing negative to positive. If you look, it actually happened. If I zoom box, I can probably get it to look a little more obvious around this part. Scale is like really important. So yeah, you can, I mean, you could probably see it before, but you can see it like a little better there. All right, so that's like a really good analysis of that problem. And those are the things you want to think about, like finding critical points. Sure, that's where it's in the domain, the derivative is 0 or undefined. But like what's happening at critical points is really what you want to be answering. So I wrote my answers to 3 decimal places. You're always going to do that. So this gets a highlight around the edges. So always use 3 decimals. Why are you doing that? Because you're going to take the AP exam, and on the AP exam, all decimals must be to 3 decimal places, correctly rounded or truncated, but no one truncates. So correctly round your answer to 3 decimal places. And that's the only way you can get the points. It could be frustrating for you if no one told you that, but I am telling you that. So you don't need to be frustrated because you're going to know. Every answer that's a decimal will be to 3 decimal places, and you're going to leave it like that. If your graph wasn't showing you 3 decimals, so let's go back. Mine was, but if it wasn't showing you 3 decimals on a graph page, graphs and calculators have different settings for floats. Go to the graph page, press menu, press 9, change your float to 6, and then scroll down and press OK, or just press enter, I guess you could. It should ask you if you want to make it the default. If you changed anything, say yes. You want to make that your default for all new documents and this document and forever, and just kind of like leave it. All right, let's see what else is on this page. Back to the notes and keep going because there's not a lot to do on the rest of this page. So I think it would be a good idea to just like finish it. So float 6, you'll see enough decimals. Definitely do that. I don't want to hear about it later if you didn't do it and you're like, why is this now happening to me? All right, let's see. So this graph looks very familiar. All right, so this is the graph of f of x. So I should have said that. Graph of f of x. Okay, so it's a graph of f of x. List the points at which f prime is equal to 0. All right, so we already did this exercise, right? F prime is equal to 0, where you have a max or min, and it's smooth, right? So here at B, at C, not D or E, F looks good, G looks good. They're like the nice smooth points where you wouldn't, K was a little debatable, but we decided it was. L, M. And I said KLM is some sort of like airline or some, maybe it's an airline. BCFG, BCFG, HKLM, HKLM. All right, the points at which f prime is undefined. So you can't really draw on a tangent line there because the tangent line doesn't exist at those points. So we can't do that, but what we could do is we could circle them, and so that's what I usually do. So derivative definitely doesn't exist there. On a roller coaster, you're gonna have a bad time, like a really bad, like a last roller coaster ride you ever take type of time. So D, E, and J are our answers here. D, E, and J. And we already know, like, we're searching for relative maximums and minimums, and then we just decide, like, is this a maximum because the derivative was 0 and changed from positive to negative? Is this a minimum because the derivative didn't exist and changed from negative to positive? Like, those are the thoughts you want to start having. At which point on the interval does f of x take its absolute largest value? Okay, absolute largest value is definitely happening at L. That's by far the biggest value. So I'm going to say that I'm just going to say L. I don't really know why there's so much space there. And then absolute minimum value is the next question. And where does that happen? That happens at D. Okay, so these both happened at critical points, but they could have happened at A or N, because endpoints could be absolute maximums or minimums. They cannot be relative, but in this case, it didn't work out, so it's just D. All right, looking at this, there's like nothing else to do really, but I feel like because I'm here and I want to, what I'm gonna do is I'm just gonna, like, let's think about the derivative. All right, so where would the derivative of this thing be negative? So the derivative of this thing would be negative here. Wow, that's really big. Let's go a little smaller. Let's go with this. All right, so derivative would be negative here. The derivative would be negative here. The derivative would be negative here, and here, and here. So should I make a key for this? I probably should. And here. Okay, so let's say this is f prime less than 0. Okay, now where would the derivative have been positive? So the derivative would be positive here, and here, and here. So we already did where the derivative is equal to 0. We did where the derivative is undefined. So just kind of going through, we're seeing if we can like get better at reading graphs, right? So this is f prime is greater than 0. All right, where is f of x concave up? So concave up means the tangent line is below the curve. I need like a pretty different color for this so that we can like be sure of what we're doing. So concave up. So here, this is gonna be concave up. All right, so you're just looking, you're visually seeing like, where is this thing concave up? Where's the tangent line below the curve? So I'm not gonna go over this. I'm gonna kind of go like, so here to maybe here. Okay, tangent line would be above the curve, I think, from where I just stopped until like a really long time. Lines, we'll find out, don't have concavity. So this, I think, is the next place where we're concave up is here to maybe like here-ish. There's definitely a point where the concavity changes there. That's called a point of inflection. And now where do we pick up again with concave up? I think somewhere in here there's a point of inflection, and then concave up through here. And then no concavity on a linear part, concave up. This is subtle. I don't know. I think that that's linear, but at the end there, it kind of like hooks a little bit. I think what I probably did was a linear thing until like the x-axis, and then maybe like something, I don't know, concave up. I'm gonna say concave up like here, and then here, and then somewhere in there it changes again, and then concave up. So concave up means the tangent line is below the curve. So there to there, I think. Okay, and then we should do concave down. So concave down, what would be a good color? I don't know, I'm running low on colors. Not really, I have like an infinite number, but I don't really like a lot of them. So concave, ew, what? That's not even a C. Okay, concave down. And here we go, concave down. So concave down, I'm gonna go like on this, there to there, I think for sure. Here to here. Okay, no concavity on that straight line segment. Concave down here through this grossness, and then here, and then we switch. All right, so we kind of like painted this thing up, concave down. I just wanted to do that because like we're not seeing each other, so we're not talking about this. I really like to draw a lot of graphs on the boards and just be like, tell me all about it. Concave up, concave down, increasing, decreasing, tangent lines above, below, relative max, relative min, like all these things. They're things you have to think about, but since we're not talking about it and I can't just rapid fire them at you, occasionally we have to do it in these videos. So that's what I'm doing here. I'm gonna end this one here, come back. I hope you're finding these helpful, and I will see you in the next video.